So could you tell to a non-physics audience about what is gravitational wave and why it is important to detect it?
The laws of nature, the laws of physics, say that there are only two kinds of waves that can travel across the universe, bringing us information about things that are very far away. Electromagnetic waves and gravitational waves, nothing else. Electromagnetic waves are made from electric fields, electric forces that oscillate, and they include light, radio waves, X-rays, gamma rays, infrared radiation, microwaves, ultraviolet radiation, all the things that we're familiar with, they are electromagnetic. The only other kind of wave then is the gravitational wave, and it, by contrast, is made up of a stretching and squeezing of space. So that if you have two objects that are separated from each other, they're at rest with respect to each other, and a gravitational wave goes by, they get pushed together and then apart because they're riding on the space, and the space itself is stretching and squeezing. That then is a radically different kind of a wave, and it is the only other possibility we have for studying the universe with waves. Galileo created modern astronomy when he built his little telescope, optical telescope, pointed at the sky, discovered 4 moons around Jupiter, discovered craters on our moon. What we have, and that was 400 years ago, and in those 400 years since then we have learned so very much about the universe with electromagnetic waves, almost everything we know about the universe. It's a rich universe, a beautiful universe, with fantastic pictures that you find, for example. It's electromagnetic. So gravitational waves are what LIGO has discovered, and we think of this as being like Galileo. We have created gravitational astronomy for the first time. As with Galileo, over the next 400 years, we expect that humans will discover amazing things about the universe using this new kind of wave, the gravitational waves.
Thank you. Einstein didn't believe that we could find the gravitational waves, but you believe it and you help to find it. What happened? What do you know that Einstein don't know? Is there a decisive discovery or something?
There are a lot of things we know that Einstein didn't know because that was 100 years ago. So first we know that black holes exist, that neutron stars exist. And we know that they are very strong sources of strong gravitational waves. They are the ideal source of gravitational waves when two black holes collide or two neutron stars collide. Einstein didn't know about these objects. The kinds of objects he knew about are all sources of weak gravitational waves. The second thing Einstein didn't have is modern technology. He didn't have computers, he didn't have lasers, So and with the technology that he knew about, it would be impossible to see the gravitational waves even from colliding black holes. We rely crucially on computers, on lasers, and on other pieces of modern technology.
Thank you. So, but it still took like more than 40 years to actually discover to actually detect the gravitational wave. But you know, the modern academia is kind of fast-paced and pushy and publish or perish. So do you think it's harsh or even unfair to a young physicist studying in this kind of area and project?
Well, let me first say that our project, the LIGO project, has 1,000 scientists and engineers working on it, and most of these are quite young, graduate students, PhD students, or postdoctoral students, just a few years away from the PhD. And this has been the case throughout our project, that most of the people working on it are quite young. I think it's not unfair at all because the tools, the research tools that students have learned working on this project are very powerful tools that they can take elsewhere in their careers. And so this project has been a wonderful training project for young scientists, and only a small portion of them have remained in this field, and that's fine. They've been very well trained with a very interesting project and fabulous technology, and they have now taken it off and applied it in many, many other areas of science and the economy.
You are a theoretical physicist, but you contribute so much on the experimental side of the LIGO project. You know, some physics, like George Gamow, who once said that it's kind of a contradictory between the experimental side and the theoretical side. But you managed to do both sides quite wonderfully. So how did you manage to do it? Is there some advice or experience in it?
So I was always fascinated by physics, both theoretical physics and experimental physics. When I was a PhD student for 3 years at Princeton, I spent most of my first year in a laboratory doing nuclear physics experiments, studying atomic nuclei with a cyclotron, an instrument called a cyclotron. I did not plan to be an experimenter, but this was very interesting physics. I learned a lot about physics this way and about experimental techniques. There were two great people, great professors at Princeton who were working on gravity at the time. John Wheeler, who was a theorist, he was my advisor. He was the person who first brought the idea of black holes and with that name into physics and taught us so much about general relativity and warped space-time. And the other person was a man named Robert Dicke, Bob Dicke, and Dicke was an experimenter doing very high precision experiments trying to understand gravity from an experimental side. Although I was a theorist, I went to, Dicke had a research group with about 15 researchers in the group, and I every week went to his group's meetings and listened to the ideas that they were working on, the experiments they were working on, just became very familiar with the techniques of experimental gravity. So I did not plan to work on gravitational waves, but when I saw that Ray Weiss had invented a method to search for them that appeared that it had a good possibility to succeed, I had the advantage of this experimental background, although I was a theorist. And so I embraced the idea to work with the experimenters and did everything that I could to contribute, including on the experimental side. There are key pieces of the experiment that really require some deep theory in order to conceive and develop them, and it is in those kinds of pieces that my students and I worked. And I trained several generations of students to work in the same way, very close to experiment, but although they were theorists.
And you were also the science advisor for the Nolan's film Interstellar. Was it hard to talk to someone who had no experience in physics? And do you have some experience for physicists who want to talk to a director of a movie?
I enjoyed it very much. The people that I talked with, some of them knew a surprising amount of physics. Christopher Nolan knows a lot of physics. He's learned it all by browsing the web. Steven Spielberg's father, whom I got to know, knows a huge amount of physics. He learned it from science columns in science fiction magazines. So there are many places to learn physics. The most remarkable person was Anne Hathaway, the actress who plays Amelia Brand in the movie. Well, the first time I talked to her, her first question was, is there as yet any experimental or observational data that tell us about the laws of quantum gravity? And this is a very deep question that you would normally only expect physicists to ask. But she is a curious person, learns about things around her, and somehow she had heard about the laws of quantum gravity, and she knew enough about science to ask this deep question. Others, Jonah Nolan, who was the initial screenwriter and who, with his wife Lisa Joy, is the creator of a TV series called Westworld that deals with artificial intelligence. Jonah knew no physics at all. I think he also knew nothing about artificial intelligence when they began to work on Westworld. But he is a man who can go in and study hard and learn. And so he went in and he studied hard for Interstellar. He spent about 6 months reading books that I fed to him to become familiar with the relevant physics. Others such as Jessica Chastain and Michael Caine, although they were dealing with some deep theoretical physics, they were interested, but they didn't have enough time to really study it. But they were still joyful and very enjoyable to work with because they're very intelligent. And we could have a good conversation. I could explain this to them, and they could explain things they knew about to me. Interesting people are interesting, even if they're not physicists.
Thank you. So I have to admit that when the movie first came out, I wrote an article and commenting on some of the science side. And later I read your book and turns out, oh, I was wrong and you were right all along. But anyway, some people say that it's a fiction, it's a movie, it's in a fictional world and you can't get every detail right anyway. So there's no point trying to argue all these fine details. Yet you put all these works, make it all into it. So why did you decide to do it?
So I wanted to make a movie that, first of all, it would be enjoyable. I wanted to have fun. It was fun. But I wanted to make a movie that would inspire people who are not scientists about science, about the beauty of science, about the beauty of the universe, about the power of science, and even some about the limitations of science. And making a movie that is as close to real science as possible while still making the movie great. It's a wonderful method to inspire people about science, and I think it was especially effective in China and Korea for that purpose. I don't know why China and Korea, but those are the countries where my book about the science of interstellar seems to have sold the most, and where I have seen great enthusiasm. So let me put it this way: the movie has sold a total of approximately 100 million tickets. How else could I, as a university professor, reach 100 million people to try to inspire them about science except through a movie like this?
True. Yeah, and you really did find a great way to reach out to all these people. But then after this, could you still enjoy other science fiction movies that are less science ones, like Star Trek?
So I enjoy Harry Potter. Harry Potter is not science fiction, it's science fantasy. It's fantastic things that are quite different from the real world, but they are set in a world that is different from ours, where magic occurs. And I can set aside real science and simply enjoy a movie about a world or a universe. The laws of physics as we know them don't exist, where magic is possible. There are many different kinds of things that are enjoyable. They don't have to be real science. But if I want to inspire people about real science, then I think the best way is a movie like Interstellar.
Yeah, true. I'm a fan of science fiction myself, and I noticed a lot of your research work seems to have great applications in science fiction. So when you were working on this thing like wormholes and time travels, were you thinking about the science fiction part, or you're just working on other things and they come out naturally?
I was not particularly thinking about the science fiction part. When I worked on wormholes and time travel, what I was trying to do is use these as tools for trying to understand pieces of the laws of physics that we don't understand well. We don't understand very well the nature of time. And so to ask the question, do the laws of physics permit time travel? That's actually a very deep question, and it enables you to focus in and try to find what is it in the laws of physics that control time travel, or that control whether time travel can exist. And as I said to a group of students after a screening of Interstellar this evening, we in this case Stephen Hawking and I, we found the piece of physics that we think actually controls whether you can have backward time travel. It's what we call the laws of quantum gravity. So to me that was a great discovery, a discovery that in order to know whether you can have time travel, we have to first understand laws of quantum gravity, and then we can use those laws to analyze time travel. And so that was the purpose and the result, the purpose of this research and the result of the research.